Good morning. I'm Scott Humphries from CALEVA Process Solutions. CALEVA is a British company. We've been established over 55 years now. We've specialised over the years predominantly in extrusion and spheronisation, but we've also moved into material characterisation as well, which is what I'm here to talk to you about today. We have a machine called a mixer torque rheometer, which you can see on the screen there, and I'll refer to it as the MTR from now on, so just so as you know what the abbreviation is. So this machine is predominantly used for material characterisation and formulation development, but it can also be used in a production environment for measuring consistency. So, for example, the previous speaker was talking about granulation. If you're making big batches of granulation over maybe an 8-hour shift or something like that, and you start getting problems with yield, then you can take samples through the course of the day and measure them using this machine, and you can see that you've got a consistent measurement there. If your yield starts to drop, you can actually physically measure the rheology of the material and see if that's changed, so you can actually see if there's anything that gives you a pointer there as to what may be going wrong. So, as I said, it speeds up development and it increases your ability for quality control. So, the machine's got 4 main components to it. You've got a mixer bowl, which is a high shear mixer, slightly different technology than what you've just seen. There's a gearbox, a syringe pump, and a laptop. So it's a very simple piece of equipment. So what we can see here is the mixer bowl. This consists of the bowl itself, a gearbox, some mixer blades, a front plate which fits on here, and a lid. So all of this can be assembled and disassembled very, very quickly, and it's very easy to clean as well. Now, the whole idea of the machine is you can run lots and lots of experiments in a short period of time, and it saves a lot of money in the fact that you use very little time and also very little material as well. So this mixer bowl here, you would typically put between 15 and 20 grams of material in. And it works by measuring the torque from the gearbox, and it transfers that along this onto a load cell and measures the torque in Newton meters from there. So when the gearbox is running and the mix is running, you can see that there's 2 counter-rotating blades here. Now the gap between the blades when they cross and the mixer bowl is only 0.5 of a millimetre, so that's where you get the shear created. This is slowed down, by the way, so it's not that slow normally. You've then got a syringe pump, which I'm sure everybody's familiar with, and that's controlled from the laptop. There's 2 different nozzle sizes depending on how much binder you want to add at each point. And then you've got a laptop which controls the MTR and the syringe pump, and it comes with our proprietary software on here. So, the MTR performs 3 different types of experiments. The first one is multiple addition. Now, multiple addition basically will measure the empty bowl of the machine first, so it gives you your 0 point. Then it will mix the dry powders together. So if you've got a formulation with 3, 4 ingredients in it, you can actually ask the machine to mix those for a certain period of time first before you start adding liquid. Now, the point of the multiple addition experiment is to establish the optimum amount of binder to add to that material to make it suitable for extrusion and spheronisation or for a granulation prior to tableting. So once you've established that amount of binder, the next thing that's important is the amount of time to actually mix that for, so you've got a homogeneous mass there. And that's what the variable mix time experiment's for. So once you've established that maybe for 20 grams of material you need to add, say, 11 millilitres of liquid to achieve a good granulation, the next thing is the machine will do the same process again, measure the empty bowl so you hit your 0 point, mix all your dry powders together, and then it will add that 11 millilitres of liquid and just mix. And you can see from what I'll show you in a minute how you can actually see the response in the torque from that, and it will give you the optimum time to mix that product for. And then the last experiment there is consistency, and this is the one that's used in production, so you can take samples and you can actually measure the actual torque reaction to that sample you've taken from your production granulation. So maybe take a sample every hour, and then you can see that you've got a consistent mix throughout your production run. So the multiple addition experiment, as the machine runs, you'll see that as the blades mix and they pass each other, you'll get a torque line like this. Now, it looks quite rough and up and down. So what the machine does is it mixes, it adds maybe 1 milliliter of binder, and then it will measure the torque response as that liquid is added to the material. And then it will add another 1 milliliter of liquid. It will mix the material again and measure the torque response with another milliliter of liquid in, and it will create a curve like this. And this is the torque response in the granulation as it's mixed. So the machine will take a mean reading of this here. So if there are any spikes where maybe you get a lump of material go between the blades, that doesn't affect the actual result of the outcome because it uses a mean value to measure. So we've got the initial stage here of the empty bowl being measured, and then we'll start adding liquid to it. And you'll see the torque increases as the liquid is added until you get to a peak here, and then you'll start to tail off as you add too much liquid to the material and it turns into a slurry. Now, the important stages on this graph that we're looking at here is we say about 80% of the peak here is the absolute optimum for extrusion and spheronisation for making pellets. And then around 30% is ideal for granulation for tablets. So it will give you a ratio of millilitres per gram of powder. And this is scalable. So if you're making an experiment on this machine with 20 grams of material, and then you move up to make 20 kilos or 200 kilos of material, the ratio of millilitres per gram is completely scalable. So it's not just a benchtop experiment, it's usable for scale up as well. This is another material here, so you can see the differences in torque response you get from different types of materials. Now this is a catalyst material, obviously not relevant to pharma, but I just put this in because you can see the difference in the shape of the graph that you get when you use different materials. So the processing window of a catalyst material to extrude it and make it into pellets is very, very small. So you can see you've got this vicious spike here. And you can imagine when you're trying to formulate to extrude and spheronize this, trying to find that 80% ratio there, you can be like 1 milliliter of liquid either side of that and it will not work. So you could waste a lot of time and a lot of expensive material trying to find that point. But with the MTR, you get that information straight away. So I put that in just so as you can see the difference in torque response with different materials. Now this is a little case study I put into the presentation as well, which is something that we had happen in Thailand. There was a manufacturer started losing, they had a very significant drop in yield in their production. Now, couldn't figure out what was wrong because they hadn't changed anything in the process at all as far as they knew. But they did find out after a while that their purchasing people had purchased MCC, which was the same spec, if you looked at the spec sheet, as the previous supplier's material, but they couldn't prove that that's what had made the difference. So we asked them to run 2 multiple addition experiments on the MTR. So you can see here, they started off by measuring the empty bowl, and then as the liquid's added, you can see the reaction, an increase in torque, and then back down to a slurry again afterwards. But the interesting thing is you can see that one material created a different torque curve to the other, and the only difference was the supplier of MCC, supposedly the same specification. But that 80% of the peak has shifted, so the ratio of millilitres per gram has changed, and that is what caused the problem. So as soon as they adjusted that, so the red line here was the second material, As soon as they adjusted the ratio of liquid to powder according to the graph that they got from the MTR, it fixed the problem. And they had no other means of finding that out really otherwise. So one quick experiment with each material with the MTR. So within 40 minutes, they found out what their problem was, and it solved the problem for them. So it can be used for all sorts of things like this. So the next one is variable mix time. As I said, once you've established the optimum amount of liquid to add for extrusion and spheronization or tableting, the next thing you need to do is you run the variable mix time experiment. So you add that amount of liquid that you've calculated into the granulation, and you will get a curve like this. So you start off by measuring the empty bowl again. It then adds the amount of liquid that you've calculated and mixes. So you see the torque increases much quicker because you've added all the liquid at the start. Now this process here is where the liquid is permeating through your formulation, and at the peak here, the peak torque reading there is where you've achieved a homogeneous mix. So you know then how many seconds to mix for. So in less than 40 minutes, you'll know the optimum amount of liquid to add for tableting and also for extrusion and spheronization. So you've got those two ratios of millilitres per gram of powder there, and you've got that in 20 minutes. And then you run your variable mix time experiment here, you add all the binder that you've calculated, and then you've got your amount of time to mix. So you'd maybe use 40 grams of material to establish that. The last test is consistency. So as I said, you can take samples out as you're producing during the day, during a shift, and then you can export the material into Excel, and you can see this is just a dramatic representation of it. So maybe you had a drop-off in yield during production and you need to find out why. If you compare the torque readings over the course of the shift, you can see it drops here, so something went wrong, and you can actually prove that it went wrong with a measurable result. So, summary is, the MTR will help you find the correct amount of binder for any given formulation. It determines the optimum mix time for that formulation, and then you can monitor your granulation quality in a production environment as well.